Hello student, welcome to IFAS. My name is Pawan Kumar Ramat and today I will tell you about Markov chain. Okay, so I made a PPT on Markov chain. So I will introduce about the PPT. So I will share about. So our topic is introduction to Markov chain. So first of all, we introduce about a stochastic process. What is a stochastic process and some important useful definitions about that. So definition of a stochastic process. So is a stochastic process is a collection of a random variable, hash valued random variable defined on a common probability space. As you know that probability space is sigma f script f and probability space p where we take a t from over a I which is a index set in which I uh, this I is represent the time horizon. Okay, so if we take the index set I as like 0 1 2 and n, this is countable, and 0 1 2 and this countable infinite, yeah, 0 to t, yeah, 0 to infinite. So in the first two case, if we see that if our first two case, uh, we have discrete time stochastic process. Okay, and in other two cases we have continuous time, because here continuous time is interval type, so this is a continuous time, so this is called continuous time stochastic process. The set S is called uh, state space of the stochastic process, where we define this S value random variable. So S is a state space. Uh, okay, so now we will introduce about some definition about stochastic process. So, if we say that what is the process of independent increment? So, process with independent increment. So, when like we take like T1, T2, Tn, we have, or we define that T1 is less than T2, is less than T3, and so on, is less than Tn minus 1 less than Tn, where all is ti belongs to our index set, where we have two types of index set, like discrete time and continuous time. Okay, so now we define that xt naught comma xt1 minus xt naught. Okay, xt2 minus xt1 naught, sorry, xt1, and so on dotted xtn minus xtn minus are all are independent of each other. Okay, where mm, most of the time we denote that t naught is equal to 0. But where what is the T naught? T naught is the minimum of T. All from all T's, or T naught is the minimum of T. Okay. Now we will define a process with stationary increment. So, like we say that if we have two state space and two time horizon, so like S1 and T1, S2 and T2, then we say that T1 minus S1 equal to T2 minus S2 have same distribution like x of T1 minus x of S1. What is x of T1? It is a stochastic process. Okay, so x t1 minus x s1 comma x t minus x2 is have all same distribution. If now we define like stationary process, so what is stationary process? If the second movement of our xt stochastic process, if there exists a second movement order of a stationary stochastic process, then expect for all t comma t plus s, where t belongs to index set I. Okay, so for all this, expectation of xt belongs to expectation of xt t plus s, both are equal. Okay, it does not depend on h, so both are equal for same covariance. We would like to define the covariance of xh comma xt is the same as covariance of xh plus h comma uh, xt plus h. Okay, this is same. Then we say that this process is stationary process. Okay, now we will define about strict stationary process. Okay, so here we talk about two uh, values like s or t or s plus h comma t plus h. But here we will define for all t belongs to I. And so this is called a strict stationary process for all t. So like t1, t2, tn plus 1, tn plus h belongs to I for all n greater than 1, have same distribution as like x of t1, comma x of tn, comma so on dot dot x t plus h, comma x tn plus h. Okay. Now as our topic is Markov chain, so we will discuss about Markov chain. So, in this chapter, we introduce an important class of discrete time stochastic process with countable yet discrete state space. Okay. So, first of all, we introduce about Markov property. So, a stochastic process has the Markov property if the conditional probability distribution of future state of the process depend only upon the present state. That is, given the present, the future does not depend on the past. Let I explain what I am saying. So let's suppose this is our state space first. Then we can go either up and either down. Okay. Then if I will go again up and down, and we can go again up and down. So what I am saying that if I go here, we it's depend only this state space does not depend on this. Similarly, if I go on this state, it's depend only the past for future state. It's depend on the present state space, not to depend on past state. Okay, so I am saying that it's mean that of xt plus 1. Okay, like if I say that this is my xt plus 1, this is my xt, and this is my xt minus sorry xt, okay, t minus 1. Okay, so uh, we said that our xt plus 1 is it does not depend upon xt minus 1 comma x1 so on order comma x0. It does not depend on past value, it depend on only present value, which is xt. Okay, so I hope it's clear what is Markov property. Markov property is that our state future state, it's depend only present value, not depend on past values. Now we will define a definition of Markov chain. So let x naught comma x1 comma x2 be a sequence of discrete random variable. Then okay, so this is a discrete sequence of random variable. Then x0, x1 x2 is a Markov chain if it satisfies the Markov property. Okay, if this is satisfy Markov property, then it's called Markov chain, otherwise not. Okay, so what is the Markov property? That probability of xt plus 1 equal to s is depend on given that xt is equal to xt comma x on dot x not equal to s naught. What is s is a state space. Okay, so this is equal to that this depend on only present value, not on past value. So probability of xt plus 1 is equal to s given xt is equal to st. It's depend on this, not on past value. So this is satisfy a Markov property. So this is called Markov chain for all t equals to 1 to so on dot dot, and for all state space. Okay, if I define what is a time homogeneous Markov chain. Okay, so there is a two type of Markov chain: time homogeneous or time non-homogeneous. Okay, so a Markov chain Xn is said to be time homogeneous if the following hold. What is the meaning of this? If this Markov chain probability of Xn equal to j given Xn minus 1 equal to I, same as probability of x1 equal to j given x not equal to I. This is meaning of that कि, it's not depend on time on which state you have. Probability of being all state is the same as probability of xn given xn minus 1 equal to. Similarly, probability of xn minus 1 given j given xn minus 2 equal to I for all is equal to like probability of x1 given equal to j given x not equal to y. All have probability same. It does not depend on time. So what is the meaning of time? Here is it does not depend on n. मतलब n is the what is the n? N is the state, which like x n. We have at state space s. So n. So if I say x5, so we add state space 5. So it does not depend on which on you state. So it does not depend n. So if we do not like this p n I j, so we can denote it by pij because it does not depend on n. So we define like this. Okay. So this is called time homogeneous if it does not depend on n. Now we define a transaction matrix. Okay. So the transaction matrix describe the Markov chain. What is the transaction matrix? Transaction matrix describe the Markov chain is called the transaction matrix. Okay, the matrix which describe the our Markov chain, like if I explain by example. So like I have a state. This is state 1, this is state 2. Okay, we are going forward, we are going to backward, and this is state 1 to 1. Okay, so in this example we are saying that a matrix which describe this Markov chain called transaction matrix. Okay, so if I would like to define Markov transaction matrix, so how we will define? So we will define like this. Okay, so first of all, we say that the transaction matrix is usually given the symbol P. Okay, so I will like to add here that this is equal to P. P equal to. Okay. This is called transaction matrix. So here there is some condition. What is condition? The row sum is equal to 1. Okay. So here row indicate, what is the row indicate? Here row indicate the current state and column indicate the transaction. Okay. So for example, if I given that the state A of the probability of going to next state A. So like our example, if we are at state 1 and what is the probability of the going state 1 again. Okay, so like if we say that's 0.3, so the what is the probability? 0.3. So this is saying that you are in at state 1 and the probability of going to next state A. So is S. So what is the probability? We define S. Okay. And given state A, you are going to next state A dash. Okay. You are going to A dash. So in our example, if we say that we are going to 1 to 2. So what is the probability of this? Like we define 0.7. Okay, so we going to this. So here we generally introduce about that, not by proper example. Okay, we discuss this later. So we say that what is the probability? R. Okay, so from state A to A dash is probability is A. So probability is R. Okay, and here we notice that the sum row sum equal to 1 because if there is probability s, then we have to row sum is 1. So what is the probability of this? 1 minus s. Similarly for 1 minus r. Okay, or this matrix is called P. If of such a square matrix with probability, okay, as entry with row sum equal to 1, if there is a row sum equal to 1, it's called stochastic matrix. This is very important. We define this is a stochastic matrix. Okay, now we define a t-step transaction probability. So let x0, x1, x2, x is so on Markov chain with n cross n transaction matrix. Now we have a n cross n transaction matrix P. Okay. So if here in this example, last we example we see that we have stated to 1, then we go next 2. This is a one step transaction probability. Okay. So if I show example, like this is our state space 1, this is second, this is third, and this is fourth. Then if we go 1 to 2, this is one step transaction probability. If we go 1 2 to 3, this is one step transaction probability. But if we go 1 to 3, this is two step transaction probability. If we go 1 to 4, this is three step transaction probability. We say that there is not a finite state space, there is infinite state space. There can be like n type. Okay, so it can be n. So when we say that t step transaction probability, this means we have at state space I and we are going to state space j by at t steps. So sorry. Uh, okay, it's okay. So if we go by in our example, I mentioned here something wrong. So I would like to explain again what is the T step. So okay, it's a one step, two step, three step, four step. Okay, this is one step transition probability. This is two step. Sorry, from two to three, this is one step. But if we see that from one to three, this is two step transition probability. ठीक है? If we go 3 to 4, this is one step 3 to 4. But if we say that 1 to 4, this is three step. Okay, so t step is what is the t step? We are at state space I and we are going to state space j in j t steps. Okay, so we can say that probability of x equal to 1 given x not equal to I. Okay, this is t steps from 0 to t. This is t steps. Okay, so we can define this like probability of t I to j. Okay, it follow that probability of similarly we can say that x n plus t, if we have at state space n, we can go next t step again. So it's depend on only past value, not sorry, it's depend on present value, not on past values by Markov chain property. So it's follow that probability of x n plus t given j, it's depend only x n. Okay, not on past values. Now we define trajectory probability. So, uh, recall that a trajectory is a sequence of values x0 to xt. Because of the Markov property, we can find the probability of an trajectory by multiplying together the starting probability and the all subsequent single step probability. What I am saying that, like I have example this. Okay, this example this example. So if x not follow 3 by 4 0 1 by 4 0 0 0, then if want to find probability of trajectory for 1 2 3 2 3 4. Okay, so then what we will do, we multiply together by starting probability and all subsequent. So probability of x not equal to 1, this is a starting. Okay, so probability of x not equal to 1 is 3 by 4. ठीक है, then we multiply by probability 1 to 2. Okay, state space 1 to 2, then we define state space 2 to 3, then 3 to 4, similarly 2 to 3 and 3 to 4. So we all multiply this together, 3 by 4 into 3 by 5 into 1 into 2 by 3 into 1 into 1 by 3. By this diagram we can see, we multiply, then we get 1 by 10. Okay, this is the trajectory probability. uh, Now we will define an example. This is a random walk S, which is we will explain prove that this is a time origin. Okay, so let we define xn is summation of m barabar 1 to n ym. What is this? We say that xn is equal to y1 plus y2 plus y3 so on dot ym. Okay, so if want to find for probability of x n plus 1, this is equal to y1 plus 1 dot ym plus yn plus 1. Okay, till here this is what is this xn. So we can say this xn. Okay, so uh, if we want to find yn plus 1 is equal to what is this xn plus 1 minus xn. Okay, we subtract xn from xn plus 1. Okay, we get x yn plus 1. Okay, so xn is defined at y1 plus y2 yn. Okay, where x not equal to 0, then xn given n greater than e time origin, we will prove this. So probability of x0 equal to 0, x1 equal to y1, so on dot dot is all is greater than equal to 0. I will explain introduce some remark that the all the entry of this transaction probability is greater than 0. No negative, all are positive. Okay, remember that. So in this example, all probability uh, pi is all are greater than 0. So probability of xn plus 1 given j equal given x not equal to 0, x1 equal to y1, so on dot dot. By xn plus 1, x, as I explained that what is the xn plus 1, xn plus yn plus 1. Okay, we say that y1 plus ym is all xn. Okay, so equal to j given this, right, same thing. Then we will find the value of yn plus 1. What is the value of, as I know xn equal to I, as per this condition xn equals to I. Okay, so we put xn equals to I, then yn plus 1 equals to j minus I, we subtract this. Okay, given all is same, then we can write this yn plus 1 equal to j minus 1. Okay, by the, because it's not depend on the past value, it's depend only present value by Markov chain property. So we can write this xn plus yn equal to j given xn equals to I. Okay, so what is this xn plus yn, what is this xn plus 1 equal to j, we rewrite this xn plus 1 given j equals to xn equal to I. So we can say that this is satisfy Markov property. Hence, if this is satisfied and it does not depend on what is the state n. Okay, so it's a time homogeneous Markov chain. Now we define some state space for n steps. So for a DTMC, what is DTMC? Discrete time Markov chain. So for this, we find that P as a transition probability matrix equal to probability of xm plus n equal to j given xm equals to I. Okay, this is our transaction probability matrix. Event, what is the event? That we are state reach k from I. Okay, we reach from uh, k from I and we reach j from k. Okay, so what is the meaning of this? Uh, we are at state space I. This is k or this is j. So we reach k from I and we reach j from to k. Okay, so from k are independent due to Markov. These all are independent because of Markov property. It's depend only present value, not on past value. Okay, so we not prove this this Chapman-Kolmogorov equation. We just introduce about this theorem. So if we have probability of m plus n, then we can rewrite this is probability of into multiply of two transaction matrix, like probability of I to k of m step and k to j in n step. So we can write p m I k into p k I, so p k j in n step. Okay, let pn, what is the pn? Pn is a n step probability transaction matrix. Okay, from I to j entry. So in Chapman-Kolmogorov equation, we can say that m is equals to 1 and n is equals to n minus 1. Then we can write p m equal to 1. So p1 equals to p and p n minus 1 equals to p n. Okay, we will get this is by Chapman equation. Now I introduce some communicating class. Okay, so communicating class is what is communicating. If I have a state space I and j, okay, in the some community class, if there is some way for getting state space I to j, and there is some way to getting from state space j to state I also. What I am saying that I am saying that I have state space I and I have state space j. Okay, and in which some state space also. And I have state space I and I have state space j in which some state also. Okay. If there is a way from I to j in some step, then there is also way to going j to I. Okay. This is called commuting class. So we define this by I, this arrow to j. Okay. There is, remember that it is not necessary, need not be possible to get between I and j in single step. There can be multiple step. It's possible that it can be a single step, but there is multiple. Okay, but it all must be possible over some number of step of travel between them. Okay, as I define. So if I definition give definition, so state I and j are in the same community class if and only if I communicating with j and j communicating with I. That is if each state is accessible from the every step. ठीक है, मतलब we can go at every step state by any step. Okay, it does not depend on what on which you have. So every state is a member of exactly one communicating class. So, okay, every state is a member of exactly one communicating class. So if I say that our I is a member of communicating class, because there is we can go from state space one to one. So there all this is true that every state is a member of exactly one communicating class. Okay. So by example, if we see that this we have a diagram like this, then we will find the communicating class. Okay, so if check that we at state 1 we can go at state 3, then again 1. Okay, we can go also 1 to 1, but if I go 1 to 2, I can't go because we can, but we can come at 2 to 1. Okay, so if we check that 1 2 3 is all these three are communicating, because if I go from 1, then we come again 1. By this 1 to 3 3 to 2 3 to 2 2 to 1. Okay, so we can come at 1 again. But if I go 1 3 2 4, then we can't come again because we don't have accessible from 4 to 2. Okay, so this is not a community class. But if we check 4 and 5, we can go 4 to 5 5 to 4. This is all, both are communicating each other. Okay, so and we have two class 1 2 3 and 4 and 5. Okay, I hope you understand, because state 2 lead to state 4, but state 4 does not back lead back. Okay, we can't come again at 2. So this is different community class. Now we introduce about some another class, like a commuting class of state is closed. When is closed? If it is not possible to leave that class. Okay, the commuting class C is called if pi is equal to 0, where I belong to J, C and J belong does not C. What I am saying, if commuting class is closed, मतलब it's possible not possible to leave. So let's see, if we see that 4 and 5, we can't leave 4 and 5. We can't go at 3 state at 1, and we can't go with any other state. So 4 and 5 are closed class. Okay, but if 1 to, if we check for 1 to 3, we can go 2 to 4 but can't come. So this is not common closed class. Okay, this is open class. So by example, we see that 1 to 3 not closed class, but 4 and 5 is closed. So I give a definition also. Let a state I is said to be absorbing absorbing if the state I is closed. So if class or commuting class is closed, we say that is absorbing. Okay, this is a definition. Okay, remember that. So here we also define a definition like a Markov chain or a transaction probability P is said to be residual if I communicating with J for all I comma J belongs to S. Okay, that is chain is irreducible if the state space S is single commuting class. Okay, so remember that this is also a definition. Okay, when we say this, the or Markov chain is irreducible. Finally, give a exercise like we can we have a Markov chain and we have to find the transaction probability matrix from state space all for 1, 2, 3. Okay, and we have to find the probability of this. Thank you. I hope my all thing is clear.